between processes and threads. This lecture assumes that you have a basic concept of processes and threads. The aim is to understand the difference between processes and threads, as most students get confused among the two. The contents include the process definition and related concepts, definition of threads and related concepts, and the difference between the two. This lecture slides are sourced from and based on the operating system concepts by Silberschatz, Galvin, and Gagne. Process concept. One of the primary jobs of operating systems is to execute a variety of programs that serve user requests. For example, a batch system where user requests are submitted as batch, and such requests are known as jobs. In time-sharing systems, many user requests known as tasks are submitted, and the users feel that the system is exclusively serving their tasks. Job, task, or process are used interchangeably across textbooks, but we will use the term process. A process is defined as a program in execution phase, and each process has a program counter, a stack, a data section, and sometimes a heap. For instance, if you write a simple Hello World program, compile it and create its executable file, this executable file sitting on your secondary storage can be termed as a program as your. When you double-click or run, this executable gets a place in primary memory and starts executing from first instruction, like main in a C or C++ program as your. This program in execution phase is known as a process. The program counter contains the address of the next instruction. The stack holds the current instance or activation record of the method or function that is executing. For e.g., if at present main is executing, stack will contain an activation record of the main with all its local variables, etc. Now if main calls another function display's activation record will be pushed onto the stack. PC will have address of instruction to be executed in display. Once control returns to main, its activation record gets popped off, and main resumes execution from where it left. By loading the PC, the data segment holds global variables, shared variables, etc. If a process needs dynamic memory, it is allocated from the heap. Process state. When a process executes, it may go through many state changes, like new, when it has just been created; ready, it is waiting to be assigned the CPU; running, it has been allocated CPU and is now executing instructions; waiting, it is waiting for some event to occur. For example, I/O. Terminated. The process has finished execution. There can be many possible scenarios, like process moves from new to ready, ready to running, running to waiting, waiting to ready, ready to running, running to ready, ready to running, and eventually terminated. Process control block. Each process has a PCB which holds information required by the CPU to execute the process. The process current state. Process ID, a unique ID assigned at the time of process creation. CPU registers, like PC, SP, DS, CS. Basically, they together hold the present execution context. Memory management information like pages, frames, start location, limits, etc. Accounting information like memory usage, processing time requirements, etc. I/O status information, present environment, I/O status, etc. Process creation. If we take example of Linux, the first process is init. The init process then spawns or creates more processes, which are its children who can create more processes, resulting in a tree of processes. Fork is used in Linux to create processes. There are various ways a parent and child may share resources. Like a parent and child share all resources. For example, a parent has opened 2 files for reading and the child will inherit both these files for reading. Children may share only a subset of resources. This may happen in a server process. For example, a parent server is listening on a port, and as soon as a client request comes, it spawns a new child process to serve that request. So only a relevant port is shared to the child process. Not all parent and child may not share any resource at all. For example, a parent process creates a child process which in turn starts executing a different process by overwriting its present image. Like the shell is a process. If you run ls command, you are basically launching a new process. Exec system call will load the child's memory space with a new program. For execution, parent and children may execute concurrently, or a child may execute and parent may wait for it to terminate. Address space. A child may have its own address space or may have a duplicate address space of the parent. In a computing environment, processes may run independently, that is, they do not require any information from other processes, may not need to share resources. Cooperating processes are those that may require to share resources. They may exchange information, split tasks to achieve modularity and speed up execution. A simplest example of processes is producer-consumer, where producer produces some item S, and the consumer consumes the measure. Threads. Moving over to threads. Thread is a unit of dispatch and refers to the current context of execution. A process may have single or multiple context of execution. Threads may be user or kernel level. There are many benefits of the thread approach. Since threads share all the resources of the program, it is easy to share resources. It is economical to create or terminate a thread as compared to the process. Threads are more responsive and can better utilize multiprocessor architectures. Here is a look at single and multi-threaded process. As you can see, threads share resources like code, data, files, memory, etc., but have their own context in terms of stack and registers. Thread states. Running state. Instructions are being executed. Ready. Waiting to execute. Blocked. Blocked on some event. Thread control block. Threaded and state. A unique id for thread and its present state. CPU information. State of stack pointer and registers to save or restore the context of the thread, where it can start or resume execution. Thread priority for scheduling. Pointers to process that created the thread and other threads in the process. Difference between process and threads. Many students get confused with processes and threads. Process defines resource ownership, that is a virtual address space of the process image in all its resources. It is basically for memory protection and avoiding illegal access of another process. Thread, on the other hand, defines present context or state. A thread has own stack and storage for local variables, and all threads in the process share the resources. Traditionally, the process had a single execution path, i.e. single context, single-threaded. Multi-threading OS can execute multiple paths of execution. Concurrent execution. In a single process, the threads can enhance speed of execution, interleave operations, asynchronous processing, and support modular program structure. For example, when you are running a MS Word application, you might be typing in your text, which is one thread that enables you to write and helps you keep track of present location. In parallel, a spelling and grammar check is running to check all the spellings. You might run a print command and may be typing in parallel, which means there are two different threads for your Word programs. Many client server models too use threads. The server threads listens on the port and may spawn a thread for HTTP request, another for FTP, and so on. While booking for tickets in an online reservation system, multiple threads serve multiple clients who are trying to book tickets. Firefox uses threads for various tabs you open. Points to remember. Threads are of two types: user and kernel level OS that support threads. Scheduling and dispatch is done at thread level. If a process that owns the thread is suspended, the threads are suspended too. If a process ULT is terminated, the threads too are terminated. A process is related to resource ownership. Threads are related to present execution or context. Threads share the resources of a process that created it, and hence some concurrency control is required while manipulating shared resources. Thread is sometimes known as the lightweight process. Do give your feedback in comments and share it with your friends. Thank you.